Hi, geometry students. Today we're going to start talking about polygons in Standard 17. And we're going to name some different types of polygons and then also get into the symmetry that happens with polygons, reflectional symmetry and also rotational symmetry. So let's just look up here at the top. When we are defining polygons, this group here, these are polygons. This group is not. And some differences that we notice between them. The polygons are all closed, so they have no openings. They all have straight edges, no curves. And polygons also have no intersecting lines. So lines don't cross on the outside or on the inside. And so that is our definition of a polygon, a closed figure with at least 3 sides. So our triangles start our polygons, and the segments are connected end to end. Some specific types of polygons: equiangular. That would be a polygon that all equal or congruent angles. So all of the angles are congruent. That angular kind of gives that one away. Equilateral polygon has all equal or congruent sides. So all the sides would be the same, not necessarily all the angles. A regular polygon is one that contains both. So a polygon that is both equiangular and equilateral. So like a square that would have all sides congruent and all angles congruent. That would be an example. A couple other things that we're going to start taking a look at are the center of a regular polygon. That would be the point inside the polygon that is equidistant from each vertex. So that would be our center. And then that would be our center point. And that's going to, if we connect to each vertex, it creates this central angle that's like on the inside here. So that's formed by the 2 lines from the consecutive vertices. So the vertices that are next to each other, that's our consecutive, and they both go to that center point. And so we're going to also talk about and measure those central angles today. All right, let's get into some reflectional symmetry. Symmetry is when you can fold or reflect over and you have both sides exactly the same or equal. And then we also have our axis of symmetry. We're going to do a couple examples of that, and that is the line that we fold or reflect over. You talked about that a little bit in when you were working with transformations. So let's take a look at a couple examples. Okay, so let's look at this triangle, and we're going to draw the axis of symmetry where we could fold it and it would divide into 2 equal parts and match up equally. So our axis of symmetry would be right down the middle here. Again, if I were to fold it, I would have 2 parts. I can't draw a line of symmetry this way because then I would not have the 2 equal parts. The sides wouldn't match up. All right, on this polygon, our axis of symmetry, I have actually 2 of them. I could draw an axis of symmetry going straight down, divided in half. And if I were to fold that over, those 2 pieces would match up. I have another one. I could also draw this horizontal axis of symmetry going through. And again, if I were to fold it over that axis of symmetry, the pieces would match up. On a square, not only do we have our vertical axis of symmetry, we have our horizontal axis of symmetry. On this one, I can actually do my diagonals as well. So I have an axis of symmetry going through that direction and also this direction. So whatever axis I were to fold it on, the pieces would match up. All right, moving on, we're gonna do a couple examples where we're looking at reflectional symmetry again, and we're gonna label these as equilateral. So all equal sides. Isosceles has 2 equal sides, or scalene, no sides are equal. And then we're going to find the measure of each angle and determine how many axes of symmetry each picture has. And we have this little chart that we're going to fill out as we go. So the way that we can double check what triangles we have, you're going to need to get your protractor out to double check my numbers here. If you were to use your protractor to, let's say, measure angle A, you should see that this angle A is 40 degrees. Angle B would be 70 degrees. And then angle C is also 70 degrees. And like I said, you can double check with your protractor. And so by these 2 angles being equal, that tells me that these 2 sides are equal. And that would be our definition for an isosceles triangle here. So we have an isosceles triangle, and this would have 1 axis of symmetry. I would only be able to go right down the middle here, vertically. And if I were to fold it, those 2 sides would match up. So let's just fill in the chart here. This was our isosceles triangle. I have 1 axis of symmetry, and there are 2 angles in that triangle that are congruent or the same. Let's take a look at this. Again, get out your protractor. We can measure what type of triangle we have. This angle, if you were to measure it, would give you a 90-degree angle. This angle would be 60 degrees and a 30-degree angle. No equal angles, so this is telling me that none of the sides are equal. I have a scalene triangle here. And if we look, I can't really draw an axis of symmetry anywhere that would allow me to have 2 equal parts once I were to fold it on that axis of symmetry. So our scalene triangles have no axis of symmetry, and they also have no congruent angle. Our last triangle over here, again, if I were to go around and measure, I would see that angle A is a 60 degree, angle B would be measure 60 degrees, and angle C. So if I have an angle that all the angles are equal, that would also tell me all the sides would be congruent. This would be our equilateral triangle. And I have 3 congruent angles. All the angles are the same. And let's see how many axes of symmetry I can do here. So because everything's equal, I'm going to have more axes of symmetry. There's 1. I could also go this way. And I can also come this way. So that gives us 3 axes of symmetry. All right, and then that is our reflectional, again, where we would fold it across that axis of symmetry and the pieces would match up. So moving on, we're going to get into rotational symmetry. See if I can write small enough here. Rotational symmetry is when the object is spun but I'm not going to spin it around the whole way. So it would be less than 360 degrees. So if I do a rotation of 90 or 180, the figure or my polygon will look exactly the same. The object, so when the object is spun and it looks the same, this is what we say the polygon then has rotational symmetry. And you're going to probably want a ruler out or use the edge of your protractor here to make nice straight lines. I'm going to try my best. We're going to connect the center of each regular polygon, and notice we're only working with regular polygons here. And then we're also going to take a look at the measure of each central angle. And you only have to pick 2 of the vertices as long as they are consecutive. So ones that are right next to each other. And I'm going to draw a straight line coming from this down to my central angle, and then another one going to the other vertice. All right, and if we were to measure, so again, get your protractor. If we were to measure this angle, you should get 120 degrees. So that central angle, if you want to label it a little bit better, that one would be 120 degrees. All right, let's do another one. Same thing. Again, we pick 2 vertices that are consecutive or right next to each other. And I'm going to just draw a line from that vertex right to the center. And then a vertex that's right next to it, again, come straight through. So on this square, if I were to measure the angle, the central angle, you should get that we get a 90-degree angle in there. All right, let's take a look at the pentagon here, 5 sides. Same thing, I'm gonna pick any 2 of the vertices. So as long as they are consecutive, I could start down here if I want. I could use this angle if you wanted to come this way or this way then. So either one, as long as they are consecutive, that creates our central angle in here. So use your protractor, measure that, and that's why it's important to try to draw a nice straight line so it can be a little more accurate. You should come out that it is 72 degrees. So on a pentagon, the central angle is 72 degrees. And again, it doesn't matter what vertices I pick. So just to show you, if I were to pick, let's say these 2 up top and measure it, I'm also going to get 72 degrees. And you may start to see, again, this one would be 72 degrees. So you may be on to how we can figure that out here. We're going to see a little pattern that's happening. And then our last, or a couple more here, we got a hexagon. So let's do our central angle. And if we were to measure that, we would get 60 degrees. Okay, again, it wouldn't matter which ones I picked. If I had picked over here and made my central angle, this is also going to be 60 degrees. All right, and a pattern that you may be noticing, 60 degrees, 60 degrees. Every time, notice what happens around that central angle is 360 degrees. So you are actually cutting that or dividing it, that 360 by your number of sides, because each section that's creating that central angle is from one of the sides of your regular polygon. And so that's where we get into this formula here. The measure, this is actually theta, the Greek letter theta, and that represents the measure of an angle. And in this case, we're talking about our central angle. A lot of Greek letters used in mathematics. You've probably worked with pi, delta, and now we have theta here, measure of an angle. And our formula to figure out the central angle is that we're going to take 360 degrees and divide it by the number of sides. So if I just were to say my variable here is my number of sides. So up here, if I didn't want to draw that out and get my protractor out to measure it, I could have done 360 divided by 3. And that would have given me one central angle for that triangle. Again, this only works with regular polygons. For the central angle of a square, 360 divided by 4, that would give us 90. Here, 360 divided by 5, 360 divided by 6. And if we get to our last one, because this one would have been pretty hard to do with your protractor. Actually get a decimal here. On our heptagon, we have 7 sides here. And if you were to try to measure this with a protractor, you'll probably get somewhere around 51 and 52. But if we do the formula for it, we actually would have 360 divided by 7. And that's going to come out to 51.42. And so that would be the measure of our central angle for our heptagon. Okay, we're going to stop there for today, and I hope that gives you a good start with our polygons and our rotational symmetry and reflectional symmetry on those.